Well, in this segment, let's look at what the Maxwell theory has to say about electromagnetic plane waves, which we'll interpret as light, which we've interpreted as light. And here I'll just use the sine and cosine. It's not too horribly difficult. uh, the I actually use the cosine, looks like. And remember, the electric field could be represented. Now, this is a real field because I'm using an amplitude vector. This is a constant vector, sine k dot r minus omega t. I've left off the phase factor because it doesn't play any role in this. It'll be the same regardless of the phase factor. And I'll look for solutions of Maxwell's equations that are this form. Electric field is sine, magnetic field is this sign with different amplitudes. And what I'll do is simply plug these two into the Maxwell equation that was the curl of E is equal to minus the partial of B with respect to t. And if you take the curl of a vector of this, it requires a little bit of calculation, but it reduces to, I'll just say, this taking the curl, when I substitute this value in, I'll get k vector, the k vector here, crossed into the amplitude, and I'll get the cosine, that's the derivative of the sine argument here. So this side reduces to this expression, and the other side, well, I've got a minus sign here, so I'll pick up a minus, which turns this into a plus, and I'll get an omega here instead of and then b is when I take the derivative of it becomes the cosine, and so the right hand side becomes omega b naught cosine, and the two cosines will cancel, and I see that k vector cross E naught is equal to omega b naught. And these are the amplitudes of those two sinusoidal plane waves. And if you look at that, omega is a positive constant, and anytime you cross two vectors here, then the result is perpendicular to both of them. And so from this relationship, I can tell you immediately that the magnetic field amplitude is perpendicular to E naught, and it's perpendicular to K. So it's perpendicular to the electric field vector and perpendicular to the K vector. You can kind of tell that if I take the dot product. If I take K dot this, then well, K dot K, anytime you this resulting vector is perpendicular to both K and E, and I dot it with K, then this side vanishes, and so K dot B vanishes, and that means that K and B are perpendicular. Likewise, I can dot it with E, and this side vanishes because this vector K cross E is perpendicular to E. When I dot it to E itself, that's perpendicular, well, the dot product vanishes, and so E dot B is equal to 0, and so B naught and E naught are both perpendicular as well. In addition, I can use, for either one of them, I can get the other Maxwell equation. Again, we're in a vacuum, or not a vacuum, but in no charge. There's no charge density rho over here. And so del dot E is equal to 0. And again, I can plug in that sine function up here for E into here, take all these derivatives, and what I find this reduces to is k vector dot E vector naught times the derivative of that cosine, which is a derivative of the sine, which is the cosine. And then that I can divide out, and so I see that k dot E naught is equal to 0, and so both K and E naught are perpendicular. And I could also have del dot B equal to 0 and do the same thing. So K vector is perpendicular to B naught as well. So they're all mutually orthogonal. And so what that leads to, you have a direction that the wave is propagating. It's in the K vector, K hat. You have E has to be perpendicular to it, so there's a right angle to this wave. B has to be at right angles to both the K and E naught, so B is going to be in this direction. And so if I've got a wave that's waving in the vertical direction along this, then the magnetic field is going to be swooping back and forth as the wave propagates in the direction of K vector. So we get a picture of something like that. We can get a relationship between the amplitudes. Namely, we had this relationship that K vector cross E naught is equal to omega B naught. That's whatever that was. Right here. So you got that. And you can come here and take the magnitude of both sides. Omega's a constant, and so this really just reduces to, it's a constant and it's positive always. It's just 2 pi times the regular frequency. So omega is positive, so I can pull it outside and I get the magnitude of the B component. And here I can use the fact that the magnitude of a cross product is the magnitude of the first vector to the magnitude of the second times the sine of the angle between the two. But as we've seen, the angle between the two is they're perpendicular, so the angle between them is 90 degrees. And so one gets 1 here, and I can solve this for the electric field. If you look at that, or the magnitude of the electric field. So divide through by K, and I get that omega over K times B is just the wave velocity. So if I'm in a material, that's the velocity that light travels in that material. If I'm in a vacuum, the speed of light in a vacuum is just c, and so you see this relationship between these amplitudes. Now that's important because if I divide this side by c, and I have an electric field amplitude, you see that the magnetic field is in magnitude is 1 over c times the magnitude of the electric field. So in terms of magnitudes, the magnetic field of a electromagnetic plane wave is much weaker than the electric component by a factor of 1 over 3 times 10 to the 8th. In the normal units that we have. Same thing applies up here. Magnetic fields are much weaker in these sets of units than the equivalent electric field components. And as a result, I've really drawn this. I try to draw this more or less with similar amplitudes, but really I should have this huge, and the amplitudes of these magnetic fields as they go waving through here should be a factor of 1 times or a factor of 1 over 3 times 10 to the 8th smaller, so that wouldn't even be seeable on this form over here. So as a result, lots of times because of this relation between the amplitudes, electromagnetic plane wave is represented totally in terms of just its major component, which is the electric field component, and pretty much everything is done with that, and you ignore the magnetic field component, although it is there. Well, you may have seen that relationship between the electric field and the magnetic field, particularly for vacuum, in some of your previous classes. But that's where it came from.